Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Steve Wu of Rambus. We're going to talk today about where power is being spent in HBM. Steve, obviously HBM has gained a lot of traction over the past couple of years. So we've gone from HBM1 to HBM2, and I think we're now starting to see HBM3. But each one of those, we're now starting to deal with much more data and much more concern in almost every design about heat and also power. More data has to be moved around, more processing has to happen. And now the power budget is being split into a lot of different places. Where is the power being spent with HBM?
Yeah, it's a good question, Ed. Just like you mentioned, I mean, the world has more data and it has to be processed. And what we're seeing increasingly is more people are turning to technologies like HBM because they have to process these larger amounts of data more quickly. And it turns out that the power that is spent in an HBM memory system, it's kind of surprising. It's not necessarily where you think it's really being spent.
Let's take a closer look.
Sure.
Steve, what have you found?
Well, like we just talked about, there's this tremendous demand for memory bandwidth, and all of the high bandwidth memory technologies are evolving very rapidly, much faster than they have been in the past, really due to this increased demand. But like I mentioned, the power is spent in places that you might not necessarily think it's being spent. Turns out that when you look at some of the modern SoCs that are putting multiple memory interfaces together on the same chip, it turns out that about 25% in the high cases, up to 40% of that entire chip power budget is really being spent in the interface circuits that are used to move data on and off the chip. And a lot of that's spent in the memory subsystem. It turns out that a lot of the reason why people turn to technologies like HBM is because they're extremely power efficient, but still a large portion of that power budget is spent moving the data. If you take a look at the pie chart on the right, you can actually see a picture of a sample SoC that's talking to an HBM memory device. And there's really three main places that the power is spent. One place would be the DRAM core, where you're actually storing and retrieving the bits of information. Now, it's not surprising that it will take some energy to do that. But what is surprising is that's only about a third of the total energy that's spent in this memory system. The other two-thirds of it is spent in the act of moving that data back and forth across the wires that connect the SoC to the DRAM. And in the SoC, there's a special set of analog circuits called a PHY, and there's an analogous set of circuits there in the DRAM as well. And those analog circuits, which convert the digital data that's stored in the DRAM across to voltages that are driven on these wires and then received by the receiving PHY, and then converted back to digital signals. Turns out that those two interfaces consume a surprising amount of power. And what we found is that about two-thirds of the power in moving data back and forth between a DRAM and a processor is really spent just in those circuits used to move the data across the wires.
How important is distance in this? So how moving the processing much closer to the memory?
That's one real mantra these days, is to really try not to move data at all, or once you do move the data, try and use it as much as you can. But distance is definitely a big factor in all of this. So technologies like HBM, they're designed to be very, very high speed, but over very short distances so that you can control the signal integrity. If you have to go longer distances, it makes the problem much, much harder.
A second way of looking at this is you're also making the compute more efficient. So instead of doing the normal, send everything back and forth between the processor and memory, you do more per cycle of the processing, right?
Yeah, if you can, what you'd like to do is to try and put the processing as close as you possibly could to that memory. And really, one of the holy grails that people talk about is what if we could put processing even in the memory itself? There's a lot of challenges with doing something like that, but it definitely addresses the issue of moving data over distance. And the other side of that is, if you can reuse the data that you move over and over again, it helps you to effectively amortize the cost of moving that data in the first place.
So really what you're doing is getting much more granular in terms of how you approach the architecture, how you approach the computing itself, right?
That's right. I mean, if you think about 20, 30 years ago when people designed algorithms, they didn't necessarily think about the type of memory they were using or what its physical characteristics were. But especially in more power constrained environments and especially mobile environments, you have to think a lot about what algorithm you're using, how much data you're moving. And in some cases, you'll think about restructuring your algorithm, much like what people have done with these domain-specific accelerators for AI. They've really rethought, how much data do I really want to have moving? And then when I do move data, how do I keep it as stationary as possible once I get it there and reuse it as much as I possibly can?
So what's the solution here? I mean, you've obviously identified the channel IO power as one of the big things going on here, along with the DRAM interface. How do you solve that?
It really remains one of the more interesting challenges that exists and gets harder every generation, because each generation we try and go faster, and each generation we try and do things to reduce the power, like dropping the voltage swing was one good example. We try and make better channels, and we try and make better circuits around that too, to address the power efficiency. But one area that is getting more attention now is, as I've shown it here, the DRAM sits next to a processor. And so in this kind of configuration, the actual distance that the data will move when all is said and done to get it kind of out of the DRAM core and across the interface, across those wires and back to the processor, and then eventually to where the processing cores are, that'll be many millimeters. In some cases, up to like 10 millimeters or maybe even more, to eventually move the data from the memory core to where it's used. One area of thought is, what about trying to stack something? Maybe if you stacked the memory directly on top of the processor, then if you could do that, you could avoid a lot of that planar horizontal data movement that you see on an interposer or a PCB. And you can go from maybe 10 millimeters of distance down to hundreds of microns. And so we're talking about a significant decrease in that distance, which will vastly improve the power that's spent moving the data back and forth.
And this is the whole idea behind a lot of the 3D IC implementations, right?
That's right. Yeah, this is one of the big benefits of being able to do something like 3D. But none of these things come for free. There's a lot of challenges that come with stacking, including things like thermals. So now, instead of having the devices be a little bit further apart from each other, and you can kind of isolate them from each other, if they're directly touching and they're stacked one on top of the other, then you have to think a lot about how you're going to dissipate the heat and provide thermal reliability in that kind of solution. There's other issues that come up as well, like the ability to scale your system. Once you've got a stack, I mean, you can only build a stack so high, and there's only so many channels to move data that you can put in a 3D stack. So, can you really keep scaling bandwidth in that way? And then the last, of course, is just generally speaking, is the power efficiency of the whole system. How do you provide power to a complete stack like that? And how do you make sure that power can be efficiently distributed to all the chips that need it? So it's not really what I would consider a solved problem, but the benefits that you can see of reducing that distance are very compelling. It's just that there's some interesting technical challenges that have to get solved.
Thermal seems to be a recurring problem here, no matter how you approach this, whether you go near memory computing, in memory computing, or whether you stack the die, right? And DRAM is very susceptible to heat.
That's right. What we've seen is that people are trying to do more in a volume of space. They're trying to improve their compute density with every generation. And as you try and do more, you'll tend to dissipate more power. And so the thermals within that confined volume will get tougher to deal with. And so we've seen over the last 20 years that thermals have really become a first-class design parameter that people have to consider from the very beginning. You don't want to be discovering at the very end of your design that you have an issue and then have to go tear it all up. So we think about those things now from the very beginning of a design.
How about some of the other parasitics? Do they enter into this picture as well?
Yeah, I mean, there's all kinds of things that you have to think about, and certainly at smaller process geometries, you get more interaction between neighboring circuits and things like that. And then when you have specific IP blocks, you have to think about how good of a neighbor that IP block is going to be to the blocks that are next to it. So you have to think about things like isolating the power that goes into a particular block, things like that. So every one of these blocks now has kind of their own requirements. And again, those are all things that have to be considered when you design an SoC.
Steve Wu, as always, thanks for a great explanation.
Thanks very much, Ed.